Are you a mechanical engineer designing pipelines? Or are you a structural engineer who designs racks and bridges carrying the pipelines? Are you looking for a software solution that can do both? Then you are perfectly right here and welcome to the webinar. Dlubal Software now offers an add-on module for the design of pipelines, which is fully integrated into the three-dimensional structural analysis software RFEM, providing an easy and effective modeling, a great graphic, as well as structural analysis and design of versatile three-dimensional structures. I will show you how to model pipelines together with the required bends and tees, reducers, flanges and valves, and you will see how easy, intuitive and quick the modeling in RFEM is, and at the end of the webinar you are able to do all this by yourself. My name is Gerlin Schubert. I'm the presenter today, and my two colleagues Lukas Sühnel and Amy Heilig will help me throughout the webinar answering all your questions. This is the GoToWebinar panel. You can show and hide the control panel by clicking onto the orange arrow button on top, and you can use the chat option to ask questions. We will try to answer all the questions while the webinar is running, but don't worry if you don't manage, you definitely get an answer via email. The schedule for today. I will explain the features of the add-on module RF piping and RF piping design so that you know what you can expect from those add-on modules. And we will then have a look to an example. We will model pipelines and we will define reducers, valves and branch connections. We will have a look to load cases and define some loads, and we will do automatic combinations of loads, and we will finally have a look to the results. At the end I give you an inside view into the printout report where you can summarize all the results that you have calculated. RF piping is fully integrated into RFEM with all its advantages. You can use the graphical input of pipe and fittings. You have libraries for cross sections and materials, but also for flanges, reducers and tees. You can include insulation, lining or tin plates. Stress intensification factors are automatically calculated. Linear elastic or thermal elastic material behavior can be considered. The elongation and straightening effect, the so-called burden effect, can be also taken into account. Supporting structure and the pipeline system, they are interacting. That's a very important feature. The module is further developed, and at the moment we work on compensators and variable spring hangers. Just that you know what you can expect also in future. The module RF piping design is doing a design in accordance to the ASME, and we are working also to the European standard. So the EN 13480 Part 3 will be implemented fairly soon. You can calculate stresses due to the permanent or occasional load situations, and you can have a documentation of results in the RFEM printout report. You will see all this in the example that we are looking at now. So from the beginning up to the far end, you will also see what you get out in the printout report. So now we already go into the RFEM. And that's the structure I've prepared for today. We have two columns that are fixed at the bottom. So we have rigid supports down here. And these are double T cross sections. And we have a main beam going across, which is a hollow rectangle cross section. We have traverses on top here, and these are again double T cross sections. And you see this, I have defined an eccentricity to get the correct alignment. So I just go into one of those members to show you this, and you can edit the member eccentricity, and I have defined that the bottom of the traverse is aligned to the top of the main beam. And when I change later on cross sections in my model, then this eccentricity gets adjusted. So the beams are moving up and down according to your settings, according to the cross section you have chosen. Okay, I cancel this so that I don't want to change anything here. And I have also defined some rigid members here. These are the dashed lines you see. And I have defined some hinges. So I go into detail here. So the rigid members, they will connect the pipe that we later model. So this is the connection of the pipeline to the structure. And I allow the pipe to move along the local Z axis, which is the global X, also along the main beam. It's allowed to move, and it has to be allowed in this direction just because of thermal expansion or anything like this. And it is allowed to rotate about the axis X and Y. Okay, I cancel this as well because I don't want to change anything, and zoom out so that you see the complete structure again. I just want to do a side note on units. I'm working in metric units today because that's just what I'm used to, but it's easy to change. We have here under Edit, you have a units and decimal places dialog, and you can go in and you can change everything you like, and we have some ready-made profiles for you here. You can go in here and you can easily change between metric and imperial unit systems. So I stick to the metric, but just so that you know, it's very easy to change. So now we already start with the piping module, and we have to activate the piping module because, as I said, it's fully integrated into RFEM. We go with a right click, we go onto the model name, and we have the general data here. We open this, and in options, you activate the piping analysis. You can do some further settings in here in the edit dialog, and that's the settings piping analysis. So the design is done in accordance to the standard, to the ASME, as I said. This is set here, and in future we will have the Eurocode as well in this drop-down list. You can choose to create the combinations automatically, so load combinations or result combinations. You can also do this all manually if you prefer, but it's quite handy to use the automatic option. And below here we have two different settings which are quite important to distinguish. There is a way to use result combinations, and this has the advantage that the thermal load cases are considered more differentiated, but result combinations also have a disadvantage. You don't really can consider non-linearities because you are already on the side of results. You combine results and you do not combine loads. The second options combines loads directly. So you lose the advantage of thermal load cases. The differentiated term, they are still considered, so it's not really a problem, but the thermal load cases are not considered such differentiated anymore. And you use load combinations here. So in our case, in our example, I want to show you how to use supports that use some friction. And friction is a non-linearity which cannot be handled very well with result combinations. So this is why I'm using this option today. On the right-hand side is an option for the burden effect. We want to consider the burden effect. So the pressure in pipes leads to extension, but also to straightening, obviously. So I want to consider both, the elongation and the straightening. And I also want to consider temperature-dependent material properties. So I have to select this checkbox at the bottom here. And just a wee side note for this drop-down, here you set some default types for the branch connection. I come back to this later on and explain this more in detail. This is just a pre-setting you can do here for the branch connections, and you will see how it's actually done then later on. This is for the consideration of intensification factors. So I keep this setting here and we come back to this. So I click OK and OK again, and now you see some buttons appeared. So there is a new toolbar just for the pipes. And in here you have a button for new pipeline, new reducer, new valve, and so on. We will see most of the buttons in the example today. We get started already with defining a new pipe. So I just rotate my model. So I click onto this button, New Pipeline. A dialog appears and I can now define a cross-section. I call it main pipe because that's the main pipe which now goes, we will define it along here, across, going over the bridge, coming down, having a V extension here. So like this. We first have to define the cross-section. So I go onto import from cross-section library. And I want to use a DN, but I want to use a DN in accordance to the ASME. So, and I'm looking for a DN 200. With a wall thickness of 6.4 millimeter. That's the one I want to choose. Down here we have to define a material. So I go to create a new material. And I go to the library as well. I could define my own one, but I prefer to choose one from the library. And to make the searching a bit easier, because we have so many materials in this database here, you can filter this for metal and for steel. And if you have a look into the special applications down here, you can filter further for temperature dependent properties. And now you have only the carbon steel available, and I go for the top one, which is carbon steel A53 grade 1. So I choose this, so I click OK, OK again, and it's now written in here. And when I confirm this, I have defined the cross-section and I have defined the material. There are some more tabs available in the piping definitions. So you could define some bending of the pipe. We want to define a straight pipe today, so that's why I keep the checkbox clear. You can have some layer definitions, so we can apply some insulation. I want to apply an insulation of 50 millimeter, which with a weight of 1 kilonewton per cubic meter. And I also want to apply some plating with a wall thickness of just 1 millimeter, but far heavier this time. That's the weight of the plating. So and as I change back to 0, the thickness, just watch the weight, the line mass. So it's adjusting the line mass. That's what happens actually when you apply insulation and apply the plating. There are some stress analysis parameters, so you could consider some corrosion, but we are not going to do this here today, but these are available options you have. So I click on OK because I'm ready with the pipe definitions. Click OK again, and now you see the cross moving already, so I'm ready to choose the nodes for my pipeline. Please note the work planes that we have up here, so we get started in the work plane XZ. So my first point is the minus 4.5 meters in X direction, and the other coordinates are 0. So I click on this, then I want to go ahead horizontal to the point minus 0.5. I click again with my left mouse button, then I move up, and now you see already I move a bit further in. You see already what happens here. It creates the bends automatically. You don't have to worry about the bends. When I press the mouse wheel, I can move my graphic, and when I scroll it, I can zoom. So while clicking all this and defining the pipeline, I can still move around and change the view. So the next point I want to define is minus 0.5, still in the x direction, so I just go up vertical, up to minus 4. Oops, sorry. Here we go. That's the point minus 4. I click with the left mouse button. You see again the banding appearing. The band is appearing. So now I go far to the right hand side, just a horizontal move, up to the point 10.5 meters in x, and I keep the z coordinate with minus 4 meter. I click with the left mouse button and go now down to y and z being 0. Click again, moving horizontal to 12.5, click again, and now I change my work plane to the XY, because now I want to build an expansion bend just to handle the heat of the piping. So I change the work plane up here. I can do all this while being in this node selection mode. And now I select the next node, which is 14. I have to rotate it a bit better. Yeah, here we go. 12.5, that's where I want to go. And it's just minus 3 where I want to go. Yeah, exactly. 12.5 minus 3 and 0 in Z. Click and go horizontal to 14.5, back down, and just the last click is at 16 meters in X direction. And now I use the right mouse button to finish all this up, and now you see what happened. I click right again to finish the whole dialog of creating the pipeline, and that's just done with making the drawing of the first pipeline. I can change the view, so I can make it transparent up here, or I can even look to the wireframe model, and now I can zoom into the bend again. You see that RFEM automatically created a lot of nodes here to create the bend automatically. So back to the solid model. So that's us done with the first branch. We define 2 more pipes, 2 more branches, because I want to also show you some fittings and reducers later on. So we need a few intersections here to have some options for T's and branches. So I go ahead and I want to create another new pipeline. So I use the button up here, new pipeline. And this time I want to use a DN 150. So I create a new cross section, use a DN 150 with a wall thickness of 4.8. Here we go. That's the right one. And I keep using the same material, carbon steel A53 with a grade A. So I can just keep this, click OK, confirm this, and I don't want to define any bendings, and I don't define any layers for this pipe. I've explained this already to you. So I just confirm the dialogues, and now I have again my cross to click. Clicking on the main graphic is just one option. You can also use the dialog up here, and you can enter the coordinates directly here. And here you have some reference options. So I want to use the current coordinate system as my reference. Last node is a nice option as well, but I use today the current coordinate system, so I always have to enter the global coordinates. So I define the first pipe, which is at x minus 1.5, and the others are 0. and I apply. You just have to be careful that you don't move out of this dialog. I apply, and then I enter a new coordinate for the y direction, which is minus 3.5, and I apply again, and then I right click, and you see that I did something wrong. I missed the minus. I just go back and create the new pipeline again. The DN 150 is still available. I want to call this also, give it a name. I click OK, and again I forgot the minus. It's minus 0.500. I apply this, and then it's minus 3.5, and I apply this and use the right mouse So you see, it's really a live demonstration. Mistakes happen. So I concentrate again. I forgot this time to change the reference option. Minus 1.500. Apply. And now I change the y coordinate. And apply again and click right. And now that's it. And I do a second pipe. I keep the dialog open. So I just enter the new coordinates. It's minus 3, 0, 0. I apply, and I change the y coordinate to 3.5 plus this time, and then apply, and I click right. That's us done with the next two pipes. I click right again to close the new pipeline dialog. And now I want to show you an option in the display navigator, which you can reach here. You have the data navigator, display, and view, and I go to the display navigator. And quite far at the bottom, you can change the colors in according to some graphic options. So I can change the color in according to pipelines. And you see a panel appearing here on the right-hand side, which is like a legend showing the colors, and you have using different colors now for each of the pipes, which can be quite nice. There's just a wee side note in between. So now we are ready with all the pipes. We have to support our pipes. We have to define some support nodes. So here is the button for new nodal supports. I click onto this and I get started with a fixed support, so which is not moving in any of the three directions. So I fix the X, Y, and Z directions. I click on OK, confirm this again, and I want to hold this pipe just right beside the bend. Okay. I right click to finish this, and I can right click again and repeat the new nodal support command. So I have to define some more nodal supports. I need now one which is free in X, so it's a sliding support in X. So I clear this checkbox to make the to allow the movement in this direction. And here I want to define a support at the far beginning, at the far end. And holding it here at the end of the bends from the expansion. So, and they are now completely free in the X direction, and the color is green, indicating that these are linear supports. What I want to do is I want to change these supports and apply some friction. I did it free in X first of all because I want to show you the change in color. So green always indicates a linear support. And I now double click on them. This is a type of support. So when I added the type of nodal support, I don't only change this one, I change all of supports which are of same type. So I go in the edit dialog again and want to apply some friction, which you can find here. You see already here in the graphic the color changed to blue now, and I have to do some further settings in here, and I want to apply a friction coefficient of 0.3. Okay, and now you see all the just defined supports changed to the color blue. I didn't touch those ones. They are still fixed and they are not sliding in any direction. I want to define another nodal support which has some friction in the y direction, so it's just an analog one, but we have now friction in the y direction and not in the x direction. So again I choose the friction pz and apply a coefficient of 0.3. I confirm this and have now to select the points where I want to hold the structure, which is at the end here, then here. So the two extra pipes are held in y direction, so they are held but free to slide or have some friction in the y direction. And I want to hold this expansion here and again at the end of the bends. Okay, I click right to finish this up. So that's us done already with the main pipe, with the two additional pipes and with the supports that we needed. We can now go ahead and define fittings, reducers, flanges. So all the intersections, all the intersections need still to be defined. And I want to define a reducer here at the beginning of the main pipe. So let's get started with the reducer. If you look through, this was the new pipe. Here we have the new reducer. So it asks me to select the pipe member. So I'm going to select the pipe member. It has chosen the wrong node, it's the node 24. So you see the list of nodes up here, it's 24 and 63. I want to have it in the direction of node 24. And I want to have a smaller diameter, otherwise a reducer does not make sense. And I have the option to define it by myself, or I can go into the library and have the length and the eccentricities defined by a special type of reducer, and that's what I'm going to do. So it's already kind of preset. So because this is all set, so I have a DN200 and a DN150, there's not much of an option. That's good in one point, so I'm going for an A type and confirm this. And now the length is already set and the angle is set, and I just have to define where I want the DN200, so the original pipe, where I want it to be started. So I can confirm this, and now you can watch the graphic changing. Here you go. That's the first reducer that we have defined. And we can already go ahead and define a valve. So I want to define the valve on this position over here, so this member. And we have a look to the buttons again, so new pipeline, new reducer, and here's the valve coming. The new valve, I go into this, again it asks me to select the pipe member. I click on the pipe. So in here I want to have the start at 300 and the length of 500. And I want to define some flanges. I want to have a flange coming from node 67, and I want to have a flange coming from the other side as well. And here again you have the choice between it to define it manually, or you can go into the library and choose some matching flanges. And here I want to choose a DN200 flange in combination with the PN16, and I want to have a plate flange for welding. So you have many options here, just choose the one you need. Okay, and when I just want to have the same flange on the other side, I can use the equal sign here and set the same flange to all my endings. When I have a more difficult intersection where more pipes are coming, then this is quite easy, quite nice to use the equal sign. Okay, so watch the graphic. I confirm this dialog, and our valve and the two flanges appear. Okay, moving ahead to a more complicated intersection, which is here. So we have 3 pipes coming here and intersecting. So I want to define a 3-way valve, which is the next button. So we were using this one, new valve, and the next one is a 3-way valve. So I click onto this, and again, I have to select something, and this time it's not a member, it's a node. So it might be sometimes easier to change to the wireframe so that you can see the node better, and it's this node that I just select. It's here listed now, the node 63. And it recognized all the pipe cross sections that are here in this position, so the DN 150 and the DN 200. And I just have to define my flanges. That's basically, I have to define the length. Yeah, that's what I was looking for. I have to define the lengths, and then we define the flanges. So it's quite a similar input at what we have just done. I define length in all 3 directions of 300 for all the segments, and I go ahead to the flanges, and I want to apply flanges from all sides. So I go to the library, choosing a matching flange for the DN 150. So I'm choosing the same PN for the DN 150, again a plate flange for welding. I click OK. And here I have to define it again because it's a different diameter of cross-section, different diameter of piping. So I go into the library again and choose the same as we have used before. And now I can apply the equal sign to apply it to the rest of my flanges. I forgot to tell you this earlier. Here's another tab available. You can always add some additional masses. If you have, for example, a longer and more heavier wheel or anything, then you can just add some additional masses. We are not going to do this, but just to tell you all the options you have. So I confirm this, and now you don't see the graphic changing straight away because I'm still in the wireframe model. So I confirm the dialog. 3 additional nodes appeared, and now I change to the solid model, and you see what we have done. So in the same way you would define a 4-way valve. We are not going to use a 4-way valve. We don't have an intersection of 4 pipings, but it's exactly the same input you would need to do. The bends, you have a button here for new bend. I already emphasized at the beginning that when we were drawing our main pipe that the bends were automatically created. We could have chosen a different way of modeling. We could have modeled just single pipes going from one node to the next node and doing all the bends manually afterwards. But why should we do this when I just model the pipeline in one go? The bends are automatically added, which I think is a very nice option. So, but you could do it afterwards, add some more bendings when you forgot something or whenever. Here's the option for new bends. Then we have a flange, which is a flange is just to show you what a flange is. A flange is something like this. So instead of using a valve or a three-way valve as we did and add the flanges directly, you could also add the flanges later on manually. So the input is similar. So just I would need to select the pipe member, and then you get exactly the same dialog as we had it already. But it's more handy to do it all together, because usually it comes together with a valve. Now we go ahead and model our last intersection here. And there are two different options that we can use. We could use a new T. So again, here I would need to select a node. And then the input is very similar to what we've did with the valves. So we would go to the library, define a type, and we have the diameters here, and then we could define flanges. So that's a new T option. I want to show you something different. I cancel this. I want to show you the last option here on the right-hand side. I want to define a new branch connection. So again, I have to select the node. And here I'm coming back, as I promised, to the far beginning of the webinar, where we have made a presetting in the general data. I've said I come back to this later, and we have chosen here unreinforced fabricated T. So here you have some pre-definitions of branch connections, and this automatically adds the intensification factors later on when you design the pipes. So it's much more comfortable to use the branch connections instead of a simple T. So we keep going with the unreinforced fabricated T, and I show you the intensification factors later on when we look to the results. So I don't have to do anything because this is kind of a ready-made thing. I just confirm it, and it's illustrated with this ball in the center here. And now we are all done with our pipe rack and the pipelines modeling, and we've done all the reducers and fittings. So I just give you a moment to breathe and think about this, and I just drink something. So I think this was quite quickly done, a quite quick model of the whole main pipeline. We now go ahead and define our loads. We need to load our structure, we need to define load cases, we need to do a combination of loads, and so on. This is the next step in our modeling process. I go to the Edit Load Cases and Combinations dialog, which is up here. I create a new load case. So this dialog opens, and it created the first load case. Because we have activated the piping module, we have some further action categories available here. We have the pipe self-weight, the fluid pressure, and we have temperature load cases. We are going to use them all now. We get started with the pipe self-weight. So I also call it pipe self-weight. And I create another load case for the fluid. And another one for the temperature case. I want to define two temperature cases, so I call the first one just T1. Then I copy this one to save some work, so copy selected load case, and I just rename it into T2. And I'm doing a similar thing with the pressure load cases. So I want to also add some internal pipe pressure. So I call it P1, and I copy this again and define it as P2. So we have used them all the different piping load cases that are available, and I now click onto load combinations. And there is a message coming up telling me that we have to assign pressure load cases to the correct temperature load cases. That's an input the software needs from us. So I say, yes, I want to define it right now, and there's a table appearing where I can choose the T1 and assign it to the P1, and I choose my T2 and assign it to the pressure load case 2. That's all I have to do here. And now we can have a look. Another tab appeared, the piping load combinations, and it created all the load combinations automatically, and we can just double check them. Load case 1, 2, and 5, 1, 2, and 6 are in another one, and here we don't have any other weight, it's just the self weight. So then we have an operating load combination 1 with temperature 1 and pipe 1, so they are connected. That's what we've just did. We assigned them together. And we have another operating 2 load combination. And these are load combinations for our expansion. Okay, we don't get any result combinations. This is because of the option that we have chosen in the general data. I can just go back to this to remind you. It's in the data. When I click right on the model name, I come to the general data, and here we have said that we want to have load combinations only and don't want to use the result combinations. Okay. Okay. So we defined load cases and we combined them already, but we don't have any loads yet, so we have to define also loads. So there is one nice thing which really makes life easier. We have a visibility tool here. It's also available up here in a kind of reduced form, but especially here the view navigator can be used to hide some members that I'm not interested in right now. So I just want to select pipelines. So when I select this checkbox, see what happens. The whole frame gets shaded, the rack itself, and only the pipes and all the flanges that we defined are selectable. So the bridge itself, I can't select this anymore. And this is nice because I can just go over the whole model to only know. And now I can define loads. I want to define fluid in my pipe in the load case 2. So I'm going to define a new member load. And you find the fluid pipe here under the extra options, the pipe content full, and we define a weight, which is, for example, 10 for water. You could also define just a partial pipe contents. Then you would need to provide a height of the fluid as well. We want to have a full filled pipe. That's all we have to do here. I click OK, and you see the member loads appearing. I go to the next load case, just using this tiny arrow here. And I'm in load case 3 now, defining the temperature 1. So I again go to the new member load, and this time I want to define a temperature, and I want to have 20 degrees. That's us done. Please note the pipes are still selected. So, and I go to the next load case and again define a new member load and just change the 20 to the 40. So it's quite straightforward and easygoing when you keep the pipes selected. So the next one is the pressure load case. I define again a new member load, and this time I want to have some pipe internal pressure, which you find again under the extra options. Pipe internal pressure, and I want to get started with 10 bar for the first load case, and I want to have 15 bar in the second load case. So we can go through them again. Temperature, fluid in pipe, self-weight. This was quick, I think. So we just defined all the loads that we needed, and we are now ready to perform our design of the pipes. So therefore, we have to open an extra add-on module. And you find it here under add-on modules in the data navigator. You find the RF piping design. You can add this to the favorites by clicking with the right mouse button on it. Then it always appears on top. You can also open it by going to add-on modules and then go to piping and open it here, RF piping design. So this is the usual look of all our add-on modules. So it's quite a remember effect. They all look the same and they have a similar, very similar structure. We want to design all of our pipes that we have available. You could choose only some, but we want to design all of them. The standard is clear. We have set this already in the general data of our model. We want to design for all the load combinations that we created. So I just use the buttons add all load combinations. I go to materials. Here you would have the option to change the material again, just in case you calculate it and see, oh, I'm overloaded. So you don't have to go out of the module and change the material in the main program. You could do it straight away here. The same with the cross sections. You can adjust the cross sections straight from here and you don't have to go out of the add-on module. That's all we have to do as an input for the RF piping design, and we can already start the calculation. So that's us done. I think I've noticed that I did something wrong with the temperature load case. I planned to add the temperature of 60 degrees, but I just entered a 40 degree, and that's why I don't get the I expected now here a 90% stress ratio. I only get a 64% stress ratio. I will go and quickly change this. So you have seen also how to change a load on a quick way. I turn on the tables, and here you have the loads, member loads. That's what we've defined. And when I go to the correct load case, which is load case 4, here I did something wrong. Yeah, here's the 40 degrees Celsius, and I can just double click on this line and this dialog opens, and I just can change to 60 degrees and click OK. Of course, it has to delete all the results. I go back into my piping and just perform the calculation again. And now I get the expected 94% design ratio from my load combination expansion 2. You can have this in all variations: design by load combination, design by cross-section, design by pipeline, by member, by location, and so on. You get also the governing internal forces, and you have a parts list sorted by pipeline. I go now to the graphics. So I'm going out of the module but activating the results in the main graphic. So I'm using this button, and now we see I switch off my table so that it's again a bit bigger for you. We see now the design ratio, the stress ratio. And to make the view even a bit nicer, I go to the display navigator again. And here we find a section results. And in here we have members. And I can display the results on my cross sections directly. That's how it looks now. And we had the 94%, and this is in one of the bands due to the stress intensification factors that are used. And I can zoom in, and here you get the 94% that we have seen. So these are the results that you are getting out of the RF piping design. And we have now done a piping design. You might wonder what you would need to do when you are a structural engineer and want to perform a design for the actual rack, the bridges. So as I said in my introduction, the add-on module is integrated into RFEM, so you can do both. You can design the pipes and you can also design the structure which is underneath or holding the pipe. What you would need to do is, as you usually do for a structural design, you define load cases like self-weight wind and snow and some imperfections maybe. You create your usual load combinations of snow and wind, and then you finally create a result combinations where you combine your structural combinations with your piping load combinations, and result combinations can then be used in our RF steel modules. So we have many of them available. You have the common RF steel, which gives you out some stresses, or we have RF steel modules in accordance to the variety of standards, so the Eurocode 3, for example, or in accordance to the AISC. So this is how you can combine a design of pipes and the structural design of the carrying structure. The final point of today's webinar is the printout report, and this is something very important as well. So I want to show you this also. There are different options to open the printout report. You could go onto File and open a printout report. You can also decide, I want to have this graphic in my printout report anyway, especially showing my stress design ratios from my pipe design. So you can use this button up here. It's saying print graphic, and you can do some presettings here. You can either use the full page height, or you can restrict the height of the image, and you have some further options and scale factors and so on. When you click OK, you get the new printout report dialog, and you could do some further settings, or you can just open it as it is for now. I confirm this dialog and the printout report is opening up. So it opens at this position where I've added the graphic. I increase the size so that you can see it. So here you go, you can modify it a bit, you can make it a bit smaller or adjust the scalings as I said. So this was just a quick shot to show you what's actually working. And just to go through it a bit, I go to the top. So you have the content on the left hand side. You can quickly go through, and you can of course change all this. You can have your company name in the header and have a better description of your positions. But here you see in the general data, you have activated the piping, you have created combinations, you consider the burden effect, you use pressure corrections, so you use the intensification factors. So all this is listed in the printout report, and you have defined some piping materials. You have defined cross sections, layers, pipelines, and so on. You can easily delete some parts of the printout report by clicking with your right mouse button on it and just remove it if you don't need such a specific table. And you can also have a look in here, the select topics for printout reports. And here you can do some further settings. You can adjust the input, and you can adjust the results. So for example, we could change something in the design by pipeline. I could go to the details here and switch on the intermediate results, and I could also show it in a long format. That's much more detailed. Especially for piping engineers, this might be of interest. And what we can also add is the part list sorted by pipeline. So when I click OK now, we have a look to the design by pipeline. Which is here. And you see now how detailed all the results are provided into the report. Okay, one last note is that you can, when you click on the picture that we have added and holding your left mouse button pressed, you can just move it around wherever you want. So I can move it up here and have it straight under as a first thing showing in the piping, so that the printout report starts off with the piping picture. So that's all I want to show you in RFEM itself. I hope that you found it informative. You have seen that you can combine both the piping analysis and the structural analysis. You have seen how to model pipes. We have defined bends and reducers and flanges very easily and quickly. And you have finally seen the printout report, which is what you actually give away, which is the result of your analysis. I close this printout report and I go back to the PowerPoint slides just for a few closing words, but that's us done in the RFEM itself. You can always have a look on our website, which is www.dlubal.com. You can follow us online. I want to emphasize the Dlubal blog, which gives nice hints every day. We post something there and give some nice new features. And when you are looking for something, please have a look there. You find answers to most of your questions. If you still cannot find what you're looking for, just write us an email. As I mentioned at the beginning, we have an office in America, in Philadelphia, which is responsible for our customers in America and Canada. You have a separate email to write to, and you have also a separate phone, and you get a direct call to Amy Heilig. And do not forget to request your PDH credit points. So write Amy an email to request those points. And you can always have a look on our website. There are many previous webinars. We record them and you can watch them always afterwards. So the same is valid for this webinar. If something was too quick and you have to watch some parts again, just go on our website and have a look to it. Just watch it again. And the next upcoming webinar is end of September. This will be about the reinforcement and design of concrete surfaces in RFEM. So I hope to welcome some of you again. You can register online again at our website. Many thanks for your attention. Bye-bye.